So, good evening, everyone. My name is Amit Kumar Sharma. I welcome you all to the live session 5 for the course content week 5 for the course Non-Conventional Energy Resources. The course instructor is Professor Pratap Haridosar from IIT Madras. I am his TA for this course. As of now, we have covered up to week 4 content, and this class is scheduled every Monday 6 to 8 p.m. And in this class, we discussed about the previous week class content, and we solved some sample problems. So those problems can be beneficial to you to solve the current week assignment questions. Okay, so let's start for the week 5 course content. If anyone can, my content is visible to you. Am I audible? It will be great if anyone can confirm. Okay. So in this class, we have discussed about the semiconductors, p-n junctions, and what are the Fermi levels and all. So this week is connected to those parts. As in previous week, we have discussed about the solar thermal energy. But now in this week, we have discussed about the solar PV, photovoltaic. So we are in previous week, we have discussed that we are converting, we are using the solar energy to heat the liquid, okay, to heat the water, and we are using that heated water for our energy application. And we can, like, if we are concentrating the energy to generate the very high temperature of water, and we can generate the steam, and we can run the steam turbine, okay, and we can generate the electricity in this way. But now in this, using some semiconductors, using photovoltaic concepts, we can directly convert the solar energy into the electrical energy. So for that, we have to learn some basic concepts like Fermi levels, p-n junctions, what about semiconductors and all. So the week 5 classes have covered these all aspects. So let's just revise briefly about uh, these concepts, and after that we will discuss some sample questions. Okay. So I think my pointer is visible to you. So first of all, Fermi level. So it was named after the physicist Enrico Fermi. A Fermi level is the measure of energy of the least tightly held electrons within a solid. So it refers to the energy of least tightly electron, so which can move. It is important in determining the thermal and electrical properties of solid. It's very important in determining thermal and electrical properties of solids. Electrical properties means conductivity, okay? Because if the electron is movable, so it can take part in conductivity. So it will decide the electrical properties also. Fermi energy is a concept in quantum mechanics that usually refers to the energy difference between the highest and lowest occupied single particle states in a quantum system for non-interacting fermions at absolute zero temperature. Okay. So Fermi energy is concept in quantum mechanics. It's very useful in quantum mechanics and refers to the energy difference between the highest and lowest occupied single cell particle states in a quantum system for non-interacting fermions at absolute zero temperature. Fermions refer to the electrons. Okay. The value of the Fermi level at absolute zero temperature. Absolute zero temperature, or you can say 0 Kelvin or minus 273.15 degrees centigrade, is known as the Fermi energy. So basically, at 0 Kelvin, at absolute temperature, Fermi level and Fermi energy are both equal. But as the temperature changes, so these can be changed. This is not necessary to be equal. It is also the maximum kinetic energy an electron can attain at 0 Kelvin. So suppose your material is at 0 Kelvin, then the least paired electron is moving. So that is having some velocity, and the kinetic energy of that electron, the maximum kinetic energy of that electron at 0 Kelvin is the Fermi energy. So Fermi energy is constant for each solid. The highest energy level that an electron can occupy at the absolute zero temperature is known as the Fermi level. So the highest energy that an electron can occupy at absolute zero temperature is known as the Fermi level. The Fermi level lies between the valence band and the conduction band, because at absolute zero temperature, the electrons are all in the lowest energy state. So basically there are two bands, valence band and conduction band. So valence band is the band where the electrons lies, and the conduction band is the band where those electrons can take part in the electricity generation, or they can conduct the electricity, okay, or they can move freely between the external circuit. And valence band is the band where all the electrons are in their lowest state. So at absolute zero temperature, the electrons are all in the lowest energy state. Due to the lack of sufficient energy at 0 Kelvin, the Fermi level can be considered as the sea of fermions. So due to lack of sufficient energy at 0 Kelvin, Fermi level can be considered as a sea of fermions or electrons. So all the electrons are at the lowest level, valence level, in valence band. So it can be considered as the sea of fermions, above which no electrons exist. The Fermi level changes as the solids are warmed and as electrons are added to or withdrawn from the solids. So as we give the temperature, or as we give some radiation to the material, so the electrons get some energy, or after getting some energy, they can be moved to the conduction band. Okay, so they can leave the valence band. So that's how Fermi level can change according to the temperature. Now let's see about some basic about semiconductor. So a semiconductor is an electrical material. So basically semiconductor is an electrical material that exists between insulator and a conductor. So insulator is basically a material that will not conduct any electrons, okay, and conductor is a material that conduct electron very easily. So semiconductor is in between the insulator and a conductor. The most known semiconductor are silicon and germanium. Very important. These are the most known semiconductors, silicon and germanium. Semiconductors are classified further into two types: intrinsic semiconductors and extrinsic semiconductors. And the extrinsic semiconductors are further divided into p-type and n-type. So these p-type and n-type are very important. We will further discuss about these p-type and n-type. So basically, semiconductors are two types: intrinsic and extrinsic. And extrinsic is further divided into two: p-type and n-type. The major difference between intrinsic and extrinsic semiconductor is that intrinsic semiconductor is in its purest form, where it does not happen in extrinsic semiconductor. So the intrinsic semiconductor is in its purest form. It's not having any impurity. On the other side, the extrinsic semiconductors are having some impurities. Based on those impurities, uh, they behave. Okay, so we dope the semiconductor as our requirement. The extrinsic semiconductor is pure, where the extrinsic semiconductor contains impurities to make it conductive. Okay, so if you want to increase the conductivity of that particular semiconductor, we dope with some impurities, so that impurities will create some holes or provide some extra electron. So based on that, the conductivity of that particular semiconductor can be increased, or that can be sensitive to the lower temperature radiation also. Okay, so at room temperature, intrinsic conductivity is 0, while extrinsic conductivity is quite low. So when we are at room temperature, the intrinsic semiconductor has 0 conductivity, but extrinsic semiconductor having some doped material, so they are having very low conductivity. Okay. So intrinsic semiconductor and extrinsic semiconductors using doping and energy band diagrams along with the difference between the intrinsic and extrinsic semiconductor. So we will see that how the dopings are acting on the extrinsic semiconductor and are the main part for p-type and n-type. Now these are the key difference between intrinsic and extrinsic semiconductors. So the first is intrinsic semiconductor in its purest form and in extrinsic semiconductors in its impure form. Second is the intrinsic semiconductor has low conductivity, okay, and the extrinsic semiconductor it has higher conductivity than intrinsic semiconductor due to some doping. Third one, the band gap between the conduction and valence band is quite narrow. So we will discuss in our further slides about the band gap, that the band gap between the conduction and valence band is quite narrow. The energy gap is greater than that of intrinsic semiconductor. Okay, the energy gap is also greater than that of the intrinsic semiconductor. Fermi level can be found in the forbidden energy gap. So in intrinsic semiconductor, Fermi level will be between the valence band and the conduction band. It can be found in forbidden energy gap. The presence of Fermi level depends on the type of extrinsic semiconductor. So it will depend on the type, okay, because we can dope with some impurities on the semiconductor, and based on that, the Fermi energy level will depend. Temperature alone determines electrical conductivity. So in intrinsic semiconductor, only temperature is deciding the conductivity. As higher the temperature, okay, so there is high heat available, high energy is available to the electron, so they can cross the Fermi level and they can reach to the valence band. So it's only depend on the temperature. The electrical conductivity in pure semiconductor is affected by temperature as well as quantity of impurity doping. On the other side, in extrinsic semiconductor, we are providing the temperature is main reason, but the quantity of doping is also very important. Based on the doping, there are holes and electrons. So based on the quantity of impurity doping, the conductivity can vary. Pure silicon and germanium crystalline forms are examples. So please 1 second. Okay. So temperature alone determines the electric conductivity on the extrinsic semiconductors. Electrical conductivity in pure semiconductor is affected by temperature and doping. Okay. Pure silicon and germanium. Si silicon, Si germanium, Ge. Si and germanium crystalline forms are examples. So these are the examples for the intrinsic semiconductors. They are not having any doping. And impurities such as As, Sb, P, iridium, okay, aluminum, and others are doped with germanium and silicon atoms. So these are the impurities like As, Sb, P, In, Bi, Al, and the others and others are doped with the germanium and silicon atoms. Now you can see this is the valence band and this is the conduction band. So and this is the band gap Eg. So Eg is the band gap. So this is for insulator. So band gap greater than 2 electrovolt. So the band gap is greater than 2 electrovolt. It is come under the insulator. When the band gap Eg is less than 2 electrovolt, it's come under the semiconductor. So you can see that this distance, this Eg is the distance. So the Eg is more. It means that suppose there are electrons, so this electron require more energy to go the conduction band. Okay, so Eg is more. When the Eg is less, so this electron require less energy to go to the valence band. Now in metal, as we know, there are free electrons in the valence band. So there are two types. There are two possibilities. One is the partially filled bands, and second one is overlapping bands. So in the first one, the partially filled bands, you can see the valence band is half filled. Okay, so with small energy, they are already in the valence band. So free electrons are already in the valence band. And the overlapping one, the both this conduction band, you can see this boundary. You can see this is the conduction band and this is the valence band. So both are overlapping in this region. These are the two possibility for metals, partially filled and overlapping. For semiconductor, the band gap is less than 2 electrovolt, and for insulator, band gap is greater than 2 electrovolt. So our focus will be on semiconductors. Okay, so there is a filled valence band and there is empty conduction band. So for the conductivity, for to get the electrical current, we need to move the electrons from the valence band to the conduction band. Okay, so we need to reduce this band gap as much as we can, or we need, so when the radiant energy, when the sunlight falls on this material, so the energy is less, so that electrons can take that energy and go to the conduction band, and we can further transfer those electrons through external circuit and get the electrical current. So let's see how can we do this. Now comes to the solar light. So solar light we have already covered in our previous classes, that solar radiation is coming in various forms. So basically infrared, visible, and UV. So infrared is around 53% portion, visible 44% portion, and UV is 3% portion. So these are the portion of the sunlight. So we need to develop some materials that can, we need to develop some materials so that can take the infrared and visible radiation, because these are the most part of the solar radiation. UV is very less. So we need to design the semiconductor in such a way that can be sensitive to the infrared and visible lights. So the visible spectrum wavelength is 400 nanometer violet color to 700 nanometer red color, and the corresponding band gaps are 3.1 electrovolt to 1.8 electrovolt. And please focus on this band gap. It's 3.1 electrovolt to 1.8 electrovolt. And what is the electrovolt? So 1 electrovolt is the energy change that takes place when a charge equal to 1 electron. For 1 electron, you can say 1.6 into 10 to the power minus 19 coulomb is moved through a potential difference of 1 volt. So this is called 1 electrovolt. So basically, when a charge equal to 1 electron, you can say 1.6 into 10 to the power minus 19 coulomb is moved through a potential difference of 1 volt, then that is called 1 electrovolt. So the corresponding band gaps for this visible spectrum wavelength varies from 3.1 electrovolt to 1.8 electrovolt. Okay, and again this is important. Visible part is 44% and infrared is 53%. So here we can see that corresponding band gaps, again 3.1 electrovolt to 1.8, and these are insulator, semiconductor, partially filled, overlapping band. Now let's see about some major differences between the p-type semiconductor and the n-type semiconductor. So we need to we are discussing basic differences between the p-type and n-type semiconductors. So the first one is the p-type semiconductor can be formed by adding trivalent impurities. So as we know that we are doping the semiconductor with some impurities and forming the semiconductor of p-type and n-type. So it depends on the impurity. Okay. So if we want to make the p-type semiconductor, we need to add the trivalent impurities. On the other side, the n-type semiconductor can be formed by adding the pentavalent impurities. Okay. So points to be noted here. For the n-type semiconductor, we need to semiconductor can form by adding pentavalent impurities. So second difference is, so once the impurity is added, then it creates hole or vacancy of electrons. So this is called an acceptor atom. So when the material in the p-type, once the impurity is added, so it creates holes or vacancy of electrons. So it will create hole or some vacancy of electrons. So this is called an acceptor atom. So it will accept the electron, okay, or you can say the holes. And in the n-type, once the impurity is added, then it gives extra electrons. So for n-type, it gives extra electrons. So holes is denoted by the circle, empty circle, and it's denoted by a solid dot or solid circle, electrons. So it is called an donor atom. So it is having a donor atom, it is having an acceptor atom. The third group elements are trivalent impurities, or you can say the third group elements are Ga, Al, ion, etc. And for the n-type pentavalent, the fifth group elements are As, phosphorus, Bi, Sb, and etc. So you can see the other metal in the periodic table also. Now the fourth difference is the majority charge carriers are holes and minority charge carriers are electrons. So in the p-type semiconductor, we know that we are adding the impurity that will create the holes or that will create the vacancy for electrons. So the majority charge carrier will be holes here and the minority charge carrier will be electrons. On the other side, in the n-type semiconductor, we are doping with the pentavalent impurities. So that will increase the donors, or you can say that increase the number of electrons in the material. So the majority charge carrier are electrons here, and the minority charge carrier are the holes. The fifth difference is that the Fermi level of p-type semiconductor mainly lies among the energy level of acceptor and the valence band. So again, now we are looking about the Fermi levels. So the Fermi level of p-type semiconductor mainly lies among the energy level of acceptor and the valence band. So there will be acceptor we will see in the further diagrams and the valence band. So Fermi level will lie between them. And the Fermi level of n-type semiconductors mainly lies among the energy level of the donor and the conduction band. So for the n-type, the Fermi level will be between the donor and the conduction band. We will see it in detail in further. And the next difference is that the density of the hole is very high than the density of electron. So as we know that we are creating the holes, so automatically the number of holes will be more than the number of electrons. So directly the density of the hole is very high than the density of electrons. On the n-type semiconductor, the density of electron is very high than the density of hole because we are adding the electrons. And next difference is in p-type, the energy level of the acceptor is near to the valence band and absent from the conduction band. So basically the energy level will be near to the valence band and it's totally absent from the conduction band. Okay, we need to provide some energy to move it from to the valence band to the conduction band. Okay, in n-type, the energy level of the donor is near to the conduction band and absent from the valence band. So in n-type semiconductor, you know that the donor particles, the donor electrons will be near to the conduction band. The next difference is the majority charge carriers movement will be from high potential to low potential. On the n-type semiconductor, the majority charge carriers movement will be from low potential to high potential. The next difference is that when the concentration of holes is high, then this semiconductor carries the positive charge. So basically, holes refer to the positive charge, and the you can say electrons refer to the negative charge. So the semiconductor perfectly carries a negative charge because here we are having extra electrons. Okay, so they are donor extra electrons, so it's negative charge. It will give the electrons. It is positive charge. It will accept the electrons and create the vacancy for the electrons. The formation of holes in the semiconductor is called as acceptor. So in it's called acceptors. The formation of electrons in the semiconductor is called as it's not acceptor, it's donor. Donor, okay. So the formation of holes in the semiconductor is called as acceptors, and the formation of electron in the semiconductor is called donor. Now the conductivity of p-type is because of the presence of majority charge carriers like holes. Okay. So the conductivity, the p-type will be conductive due to the majority of charge carriers like holes. On the other side, the conductivity of n-type because of the presence of majority charge carriers like electrons. So these are the very important difference between the p-type semiconductor and the n-type semiconductor. Now we will look at the band gaps for this extrinsic semiconductor, and we will also look the band gap for the intrinsic semiconductor. So you can see that's 1, 2, and 3. So the 1 is for intrinsic semiconductor. So it is in purest form. It is not having any impurities. So you can say the field valence band is here and the conduction band is here, and this is the Fermi level. So there is this gap here, okay. So electrons need to get this energy so that they can move this gap, okay. But it is in its purest form. It's the conductivity will only depending on the temperature. The temperature high means the electrons have more energy, so they will go to the conduction band. But if temperature low, they are not having enough energy to jump this band gap. Okay, so it's only depending on temperature because it is in purest form. It is for intrinsic semiconductor. Now come to the extrinsic semiconductor. These are further divided into two parts. One is n-type and is p-type. So n-type, you can say that extra electrons are available near the conduction band. So you can say EF. So this is the Fermi level. So this is very small gap between these donor levels. So it's with very less, they are easily, these electrons can go easily to the conduction band and can be take part in the electricity generation, okay, for the with the external circuit. So these are donor level, okay. And for p-type semiconductor, you can say these are the acceptor. So the holes are very near to the valence band, okay. So very less Fermi level between the valence band and the acceptor level, okay. So this is n-type semiconductor, this is p-type semiconductor. And in for getting these donor levels and acceptor levels, we need to dope these with the impurities as we discussed earlier. Okay, we need to trivalent and pentavalent impurities for this n-type semiconductor and p-type semiconductors. So this is a graph showing the concentration of charge carriers versus temperature. So this y-axis is the charge carrier concentration, charge carrier concentration, and this is the temperature. As the temperature is increasing, you can say that the for the first, you can say the first regime, the low temperature charge carriers are frozen. So they are not taking part, they are frozen. But after a certain temperature, you can say there is an extrinsic regime. So in this regime, you can say the charge carrier concentration is almost constant with the temperature. So you can vary the temperature, but the charge carrier concentration is almost constant for this reason. So it depend on the doping material also. After that certain temperature, it will go to the intrinsic regime where it suddenly increases. And for the intrinsic semiconductor, you can say that at small temperature, there is no charge concentration or there is no charge that can provide the electricity. But after a very high temperature, so the electrons in the valence band have enough energy to go to the or to get the jump to the valence band. So you can say they come to the intrinsic region and the concentration is increasing. Okay. Again, briefly further discuss the intrinsic semiconductor. The charge carrier concentration depends only on temperature. It's only depend on the temperature. Conductivity depends only on temperature. So the conductivity is also depend on only on the temperature. Examples of elemental group 4 is silicon and germanium are having 1.1 electrovolt gap, uh, band gap, and germanium 0.7. And the compound group third A are GAS, INSP, okay, cadmium, Rs, and zinc, tellurium. Now the p-type is semiconductor. Charge carrier concentration depend on the dopant concentration. So as the dopant concentration is increasing, it means the more vacancy or more holes are there. So the more charge carrier are there. So the charge carrier concentration will increase. So the charge carrier concentration is also depending on the dopant concentration, and conductivity is depending on the dopant concentration because there are more holes or there are more electrons are available. So the conductivity will be more. It's also depend on the temperature also. Okay, so you can see the acceptor levels as we have earlier discussed. For N-type semiconductor, it's also similar. The charge carrier concentration depend on the dopant concentration, and the conductivity depends on the dopant concentration. So as the dopant is increasing, the availability of the holes and in N-type availability of the electrons is more. So you can see donor levels, they are easily give the electrons to the empty conduction band. So you can say this is the example of intrinsic semiconductor. So when we are providing the sunlight is striking on this metal surface on the surface semiconductor surface, you can say Eg is equals to h nu. Okay, so the one electron will jump this gap and go to the conduction band. So you can say this dot is showing the electron in conduction band. This hole is showing the valency in the valence band. This is the example of intrinsic semiconductor. Now let's do some basic questions. So that will help you to understand how to solve the assignment questions and how to relate these theory with the questions. Okay, how the questions can form based on the theory we have studied or we have discussed. Okay, and also as you learned from the class. So we will look into the some basic questions. The first one is more than one answer may be right. Okay, so more than one answer can be right. Okay, so match the following materials and band gap values. So we are having three materials A, B, and C. So A is metal, B is insulator, and C is semiconductor. And we have given the band gap. Okay, so in the band gap we have given some values like the first option is less than 2 electrovolt, Second is overlapping. Third is greater than 2 electron volt, and fourth is partially filled. So I think as we have discussed earlier in earlier slides, that these materials are having some band gaps. Okay, because we have also, as you have seen, we have seen these bands for these three materials: semiconductor, this one is, you can say, the insulator. This is metal. This is valence. This is conduction band. Conduction. Okay. This is valence. This is also valence band. This is also valence zone. This is
Your
also
screen is
conduction.
not visible.
Sorry, my screen is not visible.
Yeah, screen is not visible now.
Okay. Let me check. My audio is coming.
Yeah,
Yes,
audio
sir.
is coming perfectly.
Screen
Is it now
also
visible?
visible.
Is it visible now?
Yes,
Not
yes.
for me.
No, sir, still not.
Is
Maybe
everyone
check.
is not able to see the screen, or a particular one person is not able to see the screen?
No, sir, you are not able to.
Sorry, your sound is breaking. Please repeat.
Sir, everyone is.
Everyone not able to see. I am also not able to see. Your sound is clear. Sound is very clear.
Yes. Yes.
Okay. Now you are not able to see the screen.
Yeah. Suddenly it disappeared. Earlier it was visible. Suddenly it
Earlier,
disappeared.
okay, from last 5 minutes or 1 minute only?
Yeah. Just for 5 minutes. Just we
Okay.
started questions thereafter.
Okay. Is it now visible?
No.
No, sir, still not.
Okay. Let me reshare the PPT. Okay. Just
Yeah.
give me a moment. Okay.
Okay,
Thank you
sir.
for the information. Just let me resharing. Yeah.
Yes, your camera is on now. You are visible now.
Yeah. Is it visible now? My PPT is visible now?
Yeah. PPT is not visible, but you are visible.
Now check it, please. Is it visible now?
Yes, yes. Now is it visible, sir?
Is it visible?
Yes, yes.
Is slide changing? Slides changing?
Yes, sir. Yes, yes.
Okay. Please just give me one moment again. Is it visible now?
Yeah, yes. Yeah.
Slide changing? No? Slide is changing.
Yes, sir. It's changing.
Okay. Thank you very much for the information. If you are facing any further issue, please let me know. Okay. So let's continue the question. So we have discussed this, that for the insulator there is a particular band gap. Okay, and for semiconductor also there is a band gap. And for metal, we have discussed there were two cases. It can be partially filled or overlapping. Okay. So we have also discussed about the band gaps. So for insulator, what was for the insulator? Anyone want to tell? For the insulator, the band gap is how much? When the material considered insulator, if there is a band gap between the valence and the conduction zone, is how much?
Should be more than 2 electron volts.
Yeah, right. Very good. So if the more than 2 electrovolt is the band gap, then it go to the insulator category. If it is less than 2 electrovolt, it's go to the semiconductor category, and if we are having overlapping and partially filled, it can be metal. So now just check the options. So we can see that A can be metal, can be 2, and metal can be 4th also. Okay, overlapping or partially filled. For B, it can be 3 only. For insulator, the band gap is greater than 2 electrovolt, and for C, semiconductor, it is less than 2 electrovolt. So C is 1 only. So A2, B3, C1, and A4, B2, B3, C1. These are the correct answer. Now next question. Now let material A has a band gap value of 1.9 electrovolt. 1.9 electrovolt. Just focus on the number. It's very important. Okay. So this material. Now, what are the implication of this this gap value? So we are having 3 options. The first one is this material is transparent to parts of the visible spectrum. This material is insulating in nature, and wavelength equivalent to band gap value lies in visible spectrum. So we need to first, this material is insulating in nature. So can we, as in our earlier question, we know that if the band gap is greater than 2 electrovolt, then the material will come under the insulation category. So its statement 2 implies from this 1.9 electrovolt. This 1.9 electrovolt is more or less than 2 electrovolt. It is less than 2 electrovolt. So it will not come into the insulating nature. So this statement 2 will not implication of this 1.9 electrovolt. It is false basically. Now this material is transparent to parts of the visible spectrum, and wavelength equivalent to band gap value lies in the visible spectrum. So we have covered the visible spectrum. Okay. So the range for the visible spectrum is around 3.2 electrovolt to 1.8 electrovolt. So this is the range for the visible spectrum. So you can see that 1.9. So 1.9 is just near to the 1.8 electrovolt. It's more than 1.8 and less than 3.2. So this 1.9 is lying between the visible spectrum band gap values. Okay. So the wavelength equivalent to band gap values lies in the visible spectrum. So the wavelength corresponding to this band gap will lie in the visible spectrum. Okay. So it's 400 nanometer to 700 nanometer. So wavelength will be near about 700 nanometer. Okay. And the material is transparent to parts of the visible spectrum. Now this is very important. So this third will be correct. So suppose this is a material. So this is having a suppose band gap of 1.9 electrovolt. If any radiation is having more energy than 1.9 electrovolt, then what will happen? If the incident radiation is having energy more than 1.9, then the electron will move from the valence band to the conduction band. Okay, because the energy is more than the band gap value. Okay, but if suppose the energy is less than 1.9, energy slightly less than 1.9, then that energy is not sufficient for the electrons to jump the band gap value. So that solar radiation will directly pass through that material. Okay. So that material will act as a transparent. So there will be no changes in the material. Okay. So that will act as a transparent. So you can see the visible spectrum is 1.8 to 3.2. So you can see the values from 1.9 9 to 1.8 electrovolt. These are also part of the visible spectrum. So any radiation that is having value of 1.9 electrovolt to 1.8 electrovolt, those are still part of the visible spectrum, but they will not having sufficient energy so that they can provide the electron to energy to jump the valence band to the conduction band. Okay, so so this material will be transparent for this electrovolt values. Okay, so option A is also correct. So then this material is transparent for two parts of the visible spectrum. Okay, so the correct answer will be both option 1 and 3 are true. So because 1 is true, 3 is also true. So check the options 1 and 3. 1 and 2 are true. 2 is false, so it cannot be true. 2 and 3 are true. 2 cannot true, so it's false. 1 and 3 are true, so it is correct. Option 1 is true and the option second is false. It is also correct. Okay, because option 1 is true and second is false. So the correct answer are these two. Okay, because multiple options can be correct. Okay, whenever you do the assignments, try to check all the options. Okay, because there are 4 options A, B, C, and D. It doesn't mean that only one option can be correct. Okay, as you can see that in the question itself, there is it is not mentioned that one or more answers are correct, but the but you have to check all the statements. You have to apply your concepts, and based on that you have to select the options. Okay, because more than one options can be correct. Okay, it is very important for your assignments, because suppose just if you are doing assignments in a very fast manner, like in a hasty manner, then what will happen, you will directly tick option 1 and 3. Okay, and you will forget to mark this option, because statement 2 is also false. It's correct. Okay, so try to check all the options, otherwise you will get only partial marks. Now again, next question. We are having true false for the statements. So there is a one statement A: Fermi level lies closer to the conduction band and valence band in N type and P type extrinsic semiconductor respectively, and the band gap of metal can be changed. Okay, so we are having two options. So let's see the first. So we have this P type, this is N type. So N type was having electrons, extra electrons, or you can say the donors near the conduction band. Okay, and P type is having acceptors near the valence band. So we have seen earlier in the slides. Okay, so as I can read the statement again: Fermi level lies closer to the conduction band for N type, conduction band closer. Yeah, so correct. P type, valence band closer. So this is P type, valence band closer. Okay, so this statement is correct or true. Okay, so A combined with 1. Now check the statement B. The band gap of a material can be changed. Yeah, the band gap of material can be changed. So there are two ways by which we can change the band gap. It is based on the temperature, or we also change the doping. Okay, so temperature is not in our control. Suppose we are putting the material in the radiation, so directly if we want to change the band gap, we can do by the doping. Okay, if we dope more, so the band gap will decrease or increase based on the doping. Okay, so doping can change the band gap of a material. So B is also true. So the correct options are A1 and B1. My slides are visible or not?
Yes, sir.
Okay, thank you.
Yes, visible.
Yeah, thank you, thank you. Okay, now let's comes to the. Now there are two type of semiconductors, like direct band gap semiconductors and indirect band gap semiconductors. Okay. So in direct band gap semiconductors, the bottom of the conduction band and top of the valence band lies at the same value of K. Okay. And this electron can directly excite or de-excite by the absorption or emission of photon, and there is no phonon involvement in the process of excitation and de-excitation. So you can say this is the conduction band and this is a valence band. So they are directly overlapping each other, and if you want the electron want to go from this point to this point, so it can directly go. Okay, it can directly go. So the electron can directly excite or de-excite by the absorption or emission of photons. So these are the photon, you can say energy. Okay, energy. Okay, h nu. So the photon, like the photons are striking on the material, and the photons directly going from the valence band to the conduction band. The electrons are getting the energy and they are directly going from the valence band to conduction band. Okay. If a photon incident of energy, there is absorption, then electron of valence band will absorb this energy and excite to the conduction band. And when it de-excite to valence band, then it will emit some energy. So when it going from the valence band to the conduction band, it is getting the energy, and when it's de-exciting or when it's coming back from the conduction band to the valence band, it is emitting energy. So this is showing that absorption and this showing that emission. Okay. There is no requirement of phonon or lattice in the conservation of energy and momentum. So phonon, you can say the lattice translation. Okay. So when the lattice is the conservation of energy and momentum is considered as phonon. In next slide we will see. So the direct band gap semiconductors are used in light emitting applications like LEDs, laser. Okay. So direct band gap semiconductors are used in light emitting and like LED and lasers. And direct band semiconductors are also used for the solar application. Okay, considered over the indirect band gap because there's only photon changing. Okay. Now this is indirect band gap semiconductor. So what is happening in the indirect band semiconductor? The top of the valence band and bottom of the conduction band is lies at different values of K. So they are not overlapping at each other. There is like different values of K. Okay. So suppose this one is here and the conduction band is here. So when the electron is getting some energy, then first he will go like this and then like this. So there are two movements happening. Okay. So this is happening from photon vertical movement, and this horizontal movement is happening from the phonons. Okay. So if the electron goes from the top of the valence band to the bottom of the conduction band, it has to change its energy as well as a wave vector k. For momentum and energy conservation, there is involvement of phonon in the conservation process. If there is de-excitation of the electron, then not all the energy will be emitted in the form of photon, but some energy is emitted in the form of phonon, such that some part is transferred to the lattice and the lattice will vibrate and generate heat. So indirect band gap semiconductor is not suitable for light emission. Okay, because they will be heated. Okay, because lattice vibration are transferring in the form of phonons. So they will be heated, so they are not suitable for the light emission, because the continuous use will heat those. You can say also in this diagram, like photons, this is a photon, the vertical movement, then you have to go to the phonons. Okay, so if this this electron is going to here, then it cannot go directly. It will go like this photon, and this is phonon. This is indirect band semiconductor. This is direct band semiconductor. Now let's see a question based on this. Space band gap material is always preferred over space band gap material for fabricating A. So options are direct, indirect, or solar cell. So as I have already told you that direct band gap material is always preferred over the indirect for fabricating solar cell, because there is only photon involvement is there. There is no involvement of phonon. If phonon involvement is there, then there is also chances of heating of that material. Okay, when the temperature is low, when the electrons will de-excite, they will do the heating due to the lattice vibration. So the correct option will be direct band gap material is always preferred over indirect band gap material for fabricating a solar cell. Again, next question. The question is, conductivity of n space semiconductor depends on temperature, its space, and hence the conductivity can change by subsequently doping the material. So for which semiconductor the conductivity depend on the temperature only? Anyone wants to tell? We have discussed in our earlier slides that we are having two types of semiconductors, basically intrinsic and extrinsic. So one is having without. Sorry,
Your screen is not visible now.
not visible.
Yeah.
Is it visible now?
Still not.
Okay, I think today it's having some issue. I don't know what is. Let me reshare again. Is it visible now?
No, sir.
Give me just 10 seconds. Is it visible?
Yeah. Yes, sir. Now it's visible.
Okay. Thank you for the information. Yeah. So let's see, the band gap material is always a preferred over the space band gap material for fabricating A. I think we have covered this question. So, yeah, we were on this question. Okay. So we have discussed the two types of semiconductor, intrinsic and extrinsic. Okay. So anyone want to tell the difference? What is the basic difference between the intrinsic and extrinsic? Anyone? Okay, I'm giving you 1 minute. Please think and try to give the answer. Okay. So basically we are having two types of semiconductor. One is intrinsic and second is extrinsic. So intrinsic is in its purest form and extrinsic has having some impurities. Okay. So basically we can dope it. So by doping we can change the conductivity. It's based on the doping we can change the charge carrier concentration also. So the conductivity of an intrinsic semiconductor depends on temperature. So temperature only depends on the intrinsic, because it's only depend on the temperature. We cannot change the conductivity. But for extrinsic, we can change the conductivity. Okay. So the correct option is the conductivity on intrinsic semiconductor depends on temperature, its charge carrier concentration, and hence the conductivity can be changed with subsequently doping the material. Okay, so it's on depend on temperature, and if we dope with with any material, then will go to the extrinsic, and its conductivity will be changed. Okay. Now let's see about the PN junction. Okay, so this is a, you can say, perfectly doped, or you can say equally doped materials. Okay, this is P and this is N. So this is the interface of both. Okay, so these are vacancies for the electrons and these are the electrons. So what will happen? So some electrons will come here, and so the vacancies will be go here, or vacancy or holes will be created here, or these electrons will occupy this whole space, and at this space holes will create. So you can say, suppose these 3 row are coming here, so the plus will go here. Okay, so basically these section, you can say that it's actively participating and the remaining is neutral. Okay, and also you can see this is for P type, and for N type this is the valence band potential. Okay, this is Fermi potential near the valence band. It's a conduction band. Okay, for the N type again here. But when they are interacting, when we are forming the PN junction, then what will happen? Because they are connected now, so they are transferring the electrons and holes from P to N. Okay, so Fermi level cannot be different. So Fermi level bit will try to same. Okay, so in that case, you can see here for PN junction, you can see the Fermi level for the P and Fermi level for the N will become equal, and the potential for the conduction for the conduction band will become lower, and it will come here. Okay, you can say this is the PN junction, and for the valence band also decrease. So basically bending. So the potential is bending here. You can see that. Okay, and for this the Fermi level is becoming equal. And also these are the like space charge region. So basically if we are this is a neutral. Okay, so it's 0 value, so this is negative, so it's negative, it's coming, values coming down. Okay, after the interface it's again becoming positive, so positive, this again is neutral, so it's straight. So this is showing, this graph is showing the charge density. Okay, charge density is showing by this graph. Now this graph is showing the again the del E by del X. Okay, the slope of the charge with respect to X. Okay, so basically for this portion it's neutral, so 0. For this portion you can say it's negative, so decreasing, so this is increasing. Okay, and this is again, this is showing the voltage change with respect, voltage slope with respect to the X. Okay, so it's E, it's minus E, so this will be increasing and this will be decreasing. Okay, so these graphs are very important. Okay, so first is for charge density, second for del E by del X, and third for del V by del X. So now let's see a question based on this. In a PN junction, band bending happen when? So we have seen that band bending is happening. Okay, so we are having options like Fermi energy of the two materials is exactly the same before the junction is formed. The charge scales are the same across the junction. The Fermi energy varies across the junction when it is initially formed. The chemical potential of electrons on one side of junction is more than that in the other side of the junction. So we have seen in this graph, okay, the bending is happening when we are forming the p-n junction. So the correct answer are Fermi energy varies across junction when it is initially formed. Okay. And the chemical potential of electrons on one side of junction is more than that on the other side of the junction. So to become the equal, so the bending is coming. So correct options are this one and this one. Now label the graph as we have earlier seen. This one is denoting minus, plus, so it's denoting charge density. So this one is denoting decreasing slope, increasing slope. Okay. Del E by del x equals to rho by epsilon, and this is again showing the potential. Okay. Del square V by del x square equals to minus rho by epsilon. So the correct option is 1A, 2B, and 3C. Now let's come to the crystal structures. Okay, when we are developing, when we are talking about semiconductors, then we also need to develop the semiconductors. Okay, just give me one moment. Okay, so there are three structures you can see: A, B, C, and D. So this A is for single crystalline, B is polycrystalline, D is also polycrystalline, D is amorphous. Okay, so in single crystalline you can see that the complete semiconductor is made of a single crystal. Okay, you can, when you go from left to right, you can see that the structure is same. Okay, the crystal structure is made of single crystal. It is same. It is not changing. Okay, you can say the same plane is coming after a certain distance. Okay, it is single crystal. It is very difficult to make, but there are some methods by which we can make a single crystal. Okay, this is polycrystal. So in this, like you can see that when you from at the top end, when you are going from left to right, so the planes are same, but after a certain point it's close and planes are at oblique angle. Okay, so it's changing. This is having a particular boundary. So in this boundary, the plane are same, but after this boundary, the planes are changing. Like for this boundary, planes are like this, for this again. So it's changing. So it is like made of multiple crystals. Okay, like crystal 1, 2, 3, 4, and 5. It is made of 5 crystal structures. So it is called polycrystalline. This is also polycrystalline, but in the crystalline small form. Okay, it's like just looking similar to you, but they are not all similar. They are like, you can say the orientation is changing. It's having this type of orientation. It's having this type of orientation. But they are equal in size. Their size is different. Okay, but this is also a polycrystalline. In amorphous, like you can say it's like you can say like there is no particular structure. Okay, so here the crystal can be anywhere. Here, if you go this side, there maybe there is no it here anywhere. Okay, this is amorphous. So basically, we are having three structure: single crystalline, polycrystalline, and amorphous. So, like for making the crystalline, like we are using relatively pure sand or quartzite. So using some coke and heat, we are developing to metallurgical grade silicon, MGS. So MGS is having 98% purity, and if you want to develop for electronic grade silicons, so like in which the ppm to ppb, okay, metal. So we have again having some process like silicon solid plus 3HCl. So SiHCl3 gases plus H2, okay. So Si silicon is converted to trichlorosilane, which is purified and reduced back to the silicon. Now these are some process to convert the single crystalline. Okay. So this Kokrelski process, in which we are having like semiconductors grade silicon quartz SiO2 and crucible at 1670 degrees centigrade in an atmosphere of argon, boron or phosphorus added before melting. So you can say we are having some seed crystal, we are having giving some rotation. Okay. So there's a molten silicon, melting point is 14 degrees centigrade, and quartz crucible is inside it. Okay. We can also add the doping boron phosphorus before the melting. And when we move this rotating chuck outside from this molten silicon, then we are getting the single crystal structure. Okay. The heating coils are fixed heating coils, and they are having temperature of 1425 degrees centigrade. So basically, the melting of polycrystalline silicon and adding of dopants. Step number 1: introduction of seed crystal. Okay, growth of crystal structure. So we are moving forward this seed crystal, and rotation is also happening. So when we are moving it out, so the dopants and the silicon is adding to this seed crystal, and after coming to the like outside from this this pool of silicon, so they will start to solidify, and we are getting the single crystal, the growth of single crystal. Okay, this is the completed crystal. So solution is reducing down because the solution is going to the forming the crystal structure. Again, a different process is that float zone process. Okay, the limitation of this is that we are able to form small diameter like 150 mm due to surface tension. So this is having issue of surface tension, by which only 150 mm diameter we can form, but we can get higher purity. Okay, this is lower chuck, this is upper chuck. We are again using argon, but difference that we are moving heating coils. Okay, this is a particular molting. This is molten zone. This here is seed crystal. Okay, so this is polycrystalline silicon rod. So for the further understanding, you can see also this process in detail to read further. But this is basically the main major points are that we are having moving heating coils in this, and the diameter gained from this process is very like limited with small diameter. So surface tension issue is there, but the purity is high. Okay. And we can also develop amorphous silicon by chemical vapor deposition process. Like we can deposit the silicon using some chemical process. Okay, chemical vapor deposition process, and it can be deposited on any surface. Okay, like suppose just for example, if you want to drive your car from solar energy, then instead of installing solar plates on the roof of the car, we can directly deposit the amorphous silicon on the car's roof, and that can work as the photovoltaic cell. But it's not in practical application as of now, but just for understanding, it can deposit it on any surface. Okay, but it is having some issue, like it is having dangling bonds or defects. It is having issues. Okay, So to remove this, we can use hydrogenated amorphous silicon. So ASI bonded H by deposition from Chilean gas SiH4. So it can reduce the dangling bonds when we form using the Chilean gas. Now for forming PN junction, we are having three methods. First is ion implantation. So it's a low temperature process in which ionized dopants accelerated using electrical fields, and after the forming, annealing is required. Okay. Second is diffusion. So vapor phase deposition followed by high temperature diffusion. It can also a process. And third is epitaxy. So epitaxy is quite important. It's performed under high vacuum condition, and gaseous elements condense on the substrate wafer. Okay, so we are having some substrate of wafers, and under high vacuum condition, gaseous elements condense on that particular surface and form the PN junction. Okay. Now let's see some numericals, some questions. Okay, the first one is column 1 and column 2. So Kokrelski process is connected with. So we are having options like one is shape and size limitation due to surface tension of liquid. Primarily shape limitation due to surface tension of liquid, relatively minimum limitation with respect to size. And the for column 2, float zone process are fixed RF heating coils and moving RF heating coils. For heating coils, we have seen that this process is having fixed heating coil, and this was having moving heating coils. Okay, so A is connected with the 3 and B is connected with the 4. This option is correct. Now for from 1 and 2, so A is primarily shape limitation due to the surface tension of liquid and relatively minimal limitation with respect to size. Okay, and in float zone process, so shape and size both limited due to surface tension of liquid. But in this only shape is limited and size is minimal limitation having with respect to the size. Okay, so option A2 and B1. So these options are correct. Question number 9 is arrange the following in increasing order of their disorder. So small size crystal, single crystal material, and amorphous material. Okay. So as we have already covered in this slide that this is for single crystal, this is for small size crystal, and this is for amorphous and polycrystalline. Okay. So disorder will be very less in single crystal material. After this, small size crystal material, and then amorphous material. The correct option will be second, then first, then third. Now question number 10 is name the process which is used to manufacture PN junction by enabling gaseous elements to condense on surface of substrate under high vacuum. So which process is using high vacuum? We are having 4 options. Just in like 3 or 4 slides back, we have seen that process. That is epitaxy. It's using high vacuum. The correct option is epitaxy. So let's have some basic questions, true and false. So question number 1 is the highest occupied energy level in a metal at 0 Kelvin is the Fermi energy level. Is it true or false? We have covered this in our first or second slides. Anyone want to answer? I am giving you 2 minutes. The highest occupied energy level in a metal at 0 Kelvin is the Fermi energy level. Is it true or false?
It should be true.
Yeah. So is it true?
True, sir.
Now let's see the second question. Fermi energy represents the chemical potential of electron. Fermi energy represents the chemical potential of electrons. Is it true or false?
Yeah, it is also true.
Yeah. Okay. True. The space charge region is always of equal width on either side of p-n junction. Yeah, it's very important. The space charge junction we have we have seen in our one of slides that we are having the p-n junction, and this one was filled with the plus. This was with the minus. Okay. It's a very good question. So we have seen that it was on symmetric for one particular example. So is it asking in general like the space region, space charge region is always of equal width on either side of the p-n junction. So this is the p-n junction, okay? And suppose some electrons are taking part, so the space charge region will be like this. Suppose this is the first, okay? So suppose minus minus minus. So this is your the region which is taking part. Okay. So is it always of equal width on either side? Is it necessary? True or false?
It should be false because it's not always under field condition. It is changing, na? Forward reverse, but it's changing.
Yeah, basically it's depending on the doping actually. Okay. Suppose if you are having more doping, if you are having like a symmetric doping, so your number of holes and number of, like you can say, donors are like number of acceptor and donors are equal. Okay. If you change the doping, okay, so the number of holes may be more, or number of the electrons or number of the you can say the donors is more. So based on that, the space charge region can be changed. So it is not necessarily of equal width. It depends on the doping percentage. Okay, so it is false. Now, direct band gap semiconductors are better suited for solar cell application than indirect band gap semiconductors. We have also discussed this.
It is true.
Yeah, what was the reason?
Uh,
Hello, your sound is not coming.
not remembering what is the reason, but
Okay.
LED application and solar application are direct.
Yeah. So basically we are having like this type of structure, okay? And one was like this. I think now you will remember.
Yeah. Factor K was affecting.
Yeah. So basically here only photon is taking part, but in this case, photon and phonon. Okay. So the lattice vibration is also coming here because your electron first go from this side to here, this location, and from here, the electron has to move horizontally also. So that will move using the lattice vibrations, okay, and momentum transfer. So that will generate the heat. So that is not good for our semiconductors because if the extra heat is there, then maybe that affect the structure, okay. So the direct bandgap semiconductors are better suited for solar cell application than indirect bandgap semiconductors.
So where indirect type of semiconductors are used normally?
I think we
For
have
which
covered
applications?
in that slides. Let me check. I'm just not remembering. Okay, maybe there are some application in electronic industry. Okay, because semiconductors are used for various electronics now. So I'm not remembering the exact application. You can check the internet or some reference books. But
Maybe
there's
of
no
less efficiency use devices which
yeah
their heat losses are not of much importance. The
yeah
devices
right
may
right
be used,
yeah
not in
maybe
power
use
electronics and all.
yeah we have to check that actually yeah.
Yeah, right.
The fifth one is metals are usually transparent because of their lack of band gap. Is it true or false?
This is true.
No. Metal, what about the band gap?
Okay.
We have
No, no.
studied the band gap now. Actually, uh, we have seen the band gap for insulator, for semiconductor, and for metals. For metals, there are two types of band gap:
Yeah.
partially filled and overlapping. So in either
Yes.
case, they are having the valence electron portion are in the conduction band. Okay, so small temperature or small the band gap, there is no band gap, they are directly overlapping or partially filled. So small change of temperature will give the energy to the electron to go from the valence band to the conduction band. Okay, so they are easily conductive, so they are not transparent because of their lack of band gap, because the band gap is either overlapping or partially filled. It is false. So the correct option, the correct answers are one, the true, the highest unoccupied energy level in metal at 0 Kelvin is the Fermi energy level is true. The second is Fermi energy represents the chemical potential of the electrons. It's true. The space charge region is always of equal width on either side of the p-n junction. It is false. The fourth one, direct band gap semiconductors are better suited for solar cell application than indirect band gap semiconductors. Is it true? Yeah, true. And the metals are usually transparent because of their lack of band gap. It is false. So let's see these are the forward bias and the reverse bias. So basically you can see when the p-n junction are formed, so the electrons will come to the p side, is the n side. Okay, so when the p-n junction formed, so some electrons will come to the p side, so the vacancy will be created on the n side. So you can see the initially suppose this area is forming. Okay, so now this is further connected to this p side is connected with the positive terminal and the n side is connected with the negative terminal. Okay, so this p side is pumping the holes and this side is pumping the electron. So after some time, at the steady state, this type of will form because the holes are coming and those holes are occupying with these electrons. Okay, and they are coming in the equilibrium. So only you can see this type of arrangement will form after some time. So energy transfer is taking place like this. But in second case, when we are changing the terminal, when we are changing this to negative and this to positive, okay, so in reverse bias, what will happen? So this is pumping the electrons and this is pumping the holes. So the electrons will be more and this side holes will be more. So when more electrons are coming, then these electrons will do the repulsion. Okay, because same charge, same particle repels each other. So when the electrons are going this side, so already there are too much of electrons, so they will do the repulsion. Okay, so this will increase okay, the negative terminal, the buildup of negative charge will be on p side and the buildup of holes on the n side. Okay, and n side. Okay, so by using these we can draw the IV characteristic. Okay, so for the forward bias, you can see the voltage and the current is increasing. Okay, and for the reverse bias, you can say after this is going with the zero axis, and after a certain point it suddenly straight line. These are the IV characteristic for the reverse bias and the forward bias. So generally we are using this forward bias. Okay, so from these from the three classes from this week, we can come to this conclusion. Like it is quite challenging to produce single crystal Si silicon. We have seen the process for producing the single crystal. Okay, so it's quite challenging part. So multiple process steps are involved for making the single crystal. Okay, purity and dimension can have significant impact on cost, so it depends on the purity and dimension. If we want more purity, means the process has to be more stringent and like it's need to be more accurate, so it will increase the cost. Okay, amorphous silicon is also an option. Amorphous silicon is also an option. It can be easily formed on any surface. It's also an option, but it's need to be further checked for the efficiency and other application part. Second one is that there is significant variation in the Venn diagrams of different type of material. We have seen that the significant Venn diagrams, okay, variation in Venn diagrams, because by the doping we can change the Venn diagrams also. Interaction of material with radiation depends strongly on its Venn diagram. So it depends on the radiation. Okay, what type of the radiation, because each radiation is having associated electrovolt. Okay, so based on that, the band gap, it depend on it, the material will be transparent or the electrons of that material will be excited or not. It will depend on the radiation. Okay, so it basically depend on the electrovolt of that particular radiation. Visible spectrum is small fraction of for solar radiation. Yeah, we have seen that the solar spectrum is made of three type of radiation: UV, infrared, and visible. So basically the measure is infrared, second one is visible, and third one is UV, very less 3%. So visible spectrum is small fraction of solar radiation. So whenever we are like developing any semiconductor, then we need to do the doping and all other characteristic edge, so that that material will be able to excite for both visible and infrared spectrum. Okay, suppose your material is only exciting at the visible spectrum, then most of the solar radiation is coming in infrared portion. So you are getting only less available solar energy for your for your energy generation. Okay, so we need to make the material such that it is working for both your visible spectrum and infrared spectrum. Now there is a difference in the effectiveness with which direct and indirect bandgap semiconductors interact with radiation. And further is a PN junction can be formed using appropriately doped materials that are processed carefully. Yeah, charge, field, and potential depend on the location in PN junction, and PN junction has interesting IV characteristic. As we are changing the reverse bias and forward bias, so the IV characteristic will be changed. So I think these slides are over now. So, but still we are having some time left. So we can just quickly revise the slides. Okay, like maybe someone joined late, so we can just have a quick revision of the slides. So basically, in the first slides, we have covered the Fermi energy. So the Fermi level is the measure of the energy of the least tightly held electrons within a solid. So it is important in determining thermal and electrical properties of solids. Okay, so basically we are like just understanding the Fermi levels. Okay, the value of Fermi level is absolute zero temperature. Just the value of the Fermi level at absolute zero temperature is known as the Fermi energy. Okay, it's also the maximum kinetic energy of an electron that can attain at 0 Kelvin. Fermi energy is constant for each solid. The highest level that an electron can occupy at absolute zero temperature is known as the Fermi level. The Fermi level lies between the valence band and the conduction band because at absolute zero temperature, the electrons are all in the lowest energy state. Due to the lack of sufficient energy at 0 Kelvin, the Fermi level can be considered as the sea of fermions or electrons above which no electrons exist. The Fermi level changes as the solid are formed and electrons are added to or withdrawn from the solid. Now for semiconductor, we have seen so semiconductor basically a material that is between the insulator and conductor. So insulator is a material that is not conducting any electricity, and conductor that is having valence electron and can conduct the electricity, okay, or electric charge. So semiconductor is between the insulator and the conductor. So the most of semiconductor is known as silicon and germanium. And further semiconductors are classified in two types: intrinsic semiconductor and extrinsic semiconductor. And this extrinsic semiconductor further in divided in p-type and n-type semiconductor. Now the major difference between the intrinsic and extrinsic semiconductor is that in intrinsic semiconductor, a semiconductor is in its purest form. Okay, so it is not having any impurities in it. But on the other side, the extrinsic semiconductor is having some impurities to change the band gap values. The intrinsic semiconductor is pure, whereas the extrinsic semiconductor contains impurities to make it conductive. At room temperature, intrinsic conductivity is 0, while extrinsic conductivity is quite low. Because intrinsic conductivity is dependent on temperature. At room temperature, the radiation available at room temp at that temperature is not sufficient so that the electrons in the valence band can go to the conduction band. So the conductivity is quietly 0 at room temperature for intrinsic, but for extrinsic conductivity is quite low because some may be at room temperature also. Due to doping, they are having some electrons or can go from the valence band to conduction band. So these are the major difference between the intrinsic and extrinsic. Intrinsic semiconductor is in its purest form, and extrinsic semiconductor is in impure form. And the intrinsic semiconductor has low conductivity, and for extrinsic semiconductor, it has a higher conductivity than an intrinsic semiconductor. For intrinsic, the band gap between the conduction and valence band is quite narrow, and the energy gap is greater than that for intrinsic semiconductor. And Fermi level can be found in the forbidden energy gap. For this, the presence of Fermi level depends on the type of extrinsic semiconductor. The temperature alone determines electrical conductivity, and electrical conductivity in a pure semiconductor is affected by the temperature as well as quantity of impurity doping. So these are the band gaps. Okay, we have clear seen. These are the visible spectrum wavelength, 400 nanometer to 700 nanometer. The corresponding band gap is 3.1 electrovolt to 1.8 electrovolt. So infrared basically taking 53% of solar radiation, visible 44%, and UV 3%. And 1 electron volt is the energy change that takes place when a charge equal to 1 electron, or you can say 1.6 into 10 to the minus 19 coulomb, is moved through a potential difference of 1 volt. Okay, these are showing the band gap. Okay, so anyone having any doubt regarding in this slide, like valence band and band gap for insulator, semiconductor, metals, can ask. Anyone is having any doubt regarding this slide? Basically, this slide is showing insulator, semiconductor, and metals. Okay, for insulator, we can see that the empty conduction band and filled valence band, and there is a band gap Eg. So it is more than the band gap for the semiconductor. Okay, you can see the band gap for the semiconductor Eg is less than the band gap for Eg. So Eg is very more. So basically, the insulator is coming for a band gap greater than 2 electrovolt. Okay, so the band gap, if it's greater than 2 electrovolt, then it's come under the insulator. If the band gap is less than 2 electrovolt, then it's come under the semiconductor. Okay, and for the metals, we can see the conduction band is either partially filled or overlapping. Both the valence band and the conduction band are overlapping with each other. So it means that they are having available electrons in the conduction band. So they are very easily conducting, as we know that metals are easily conducting because they are having number of valence electron available in the conduction band. And the spectrum wavelength, we can see that 400 nanometer and the corresponding band gap is 3.1 electrovolt, and it's to 700 nanometer and the corresponding band gap is 1.8 electrovolt. Now the difference between the p-type and n-type semiconductor. So p-type semiconductor can be formed by adding trivalent impurities, and n-type you need pentavalent impurities. So once the impurity is added, then it creates hole or vacancy of electrons, or it is called an acceptor atom. Okay, for n-type, the impurity is added, then it gives extra electrons, so this is called a donor atom. The third group elements for p-type semiconductor that can be doped are Ga, Al, In, etc. And the fifth group elements are Asp, Bi, Sb, etc. The majority charge carriers are holes and minority charge carriers are electrons in the p-type semiconductor because we are doping the holes. So the majority charge carriers are holes. The majority charge carriers are electrons and minority charge carriers are holes in the n-type semiconductor. For p-type semiconductor, the Fermi level of p-type semiconductor mainly lies among the energy level of acceptor and the valence band. For the n-type, the Fermi level of n-type semiconductor mainly lies among the energy level of donor and the conduction band. Okay, the density of the hole is very high. Then the density of electron, because we are doping with the holes, density of electron is very high than the density of hole because we are doping with the electrons. So this p-type semiconductor, the energy level of the acceptor is near to the valence band and absent from the conduction band. And in n-type semiconductor, the energy level of the donor is near to the conduction band and absent from the valence band. For the p-type semiconductor, the majority charge carriers movement will be from high potential to low. For n-type, the majority charge carrier movement will be from low potential to high. For p-type semiconductor, when the concentration of holes is high, then this semiconductor carries the positive charge. The semiconductor carries negative charge. So the formation of holes in this semiconductor is called as acceptors, and the formation of electron in the semiconductor called as donors. The conductivity of p-type is because of presence of majority charge carrier like holes, and the conductivity of n-type because of the presence of majority charge carrier like electrons. So this is showing the intrinsic semiconductor, the n-type and p-type. The n-type you can say the donor levels, for p-type they are the acceptor levels. The Fermi level in between these donor levels and the conduction band, and here for valence band and the acceptor level. So again, we can revise this question. If anyone is having doubt in this question, please let me know. In this question, we have to match the materials with the band gap values to we have covered recently in our previous slides. So if anyone is still having doubt, please let me know. The correct answers are the metal is partially filled or either overlapping, and for insulator the band gap is more than 2 electrovolt. And for semiconductor the band gap is less than 2 electrovolt. Anyone having any doubt in this question, please let me know. In this we have given a band gap value for a particular material A, that is 1.9 electrovolt, and we need to check the 3 implications based on this value. Let's take 2 minutes and try to solve this question. Who just joined late, and if you are having any doubt, please let me know. I'm available here. So the correct options are statement 1, the material is transparent to parts of the visible spectrum is true because the band gap is 1.9 electrovolt and the visible spectrum is up to 1.8 electrovolt. So the spectrum in the range of 1.9 to 1.8 will not be able to give the sufficient energy to the electron in the you can say the valence bond to go to the connection bond. Okay, so the material for that particular spectrum that will be from 1.9 to 1.8 volt, 1.8 electrovolt, act as a transparent. Okay, so this material is insulating in nature. Yeah, it's false because for the insulation, if the electrovolt, the gap value should be more than 2 electrovolt, but it is 1.9, so it is less than 2, so it is not in insulating nature. And the wavelength equivalent to band gap value lies in visible spectrum. So yeah, it's correct because the visible spectrum is lies from 3.2 to 1.8. So 1.9 is in between that range. So let's see this question. If anyone is having doubt, please let me know. So the statement A is saying that the Fermi level lies closer to the conduction band and valence band in N-type and P-type extrinsic semiconductor respectively. So first of all, it is extrinsic semiconductor, and we have done the doping P-type and N-type. So what were the Fermi levels? We have discussed previously that in one case it is donor and one case it is acceptor. So try to recall those statements and try to find answer. And second option, the statement is the band gap of a material can be changed. So can we change the band gap of material by doping? Yeah, yes, we can change. So the accepted answer is A1, B1. So Fermi level lies closer to the conduction band and valence band in N-type and P-type extrinsic semiconductor respectively, and the band gap of material can be changed. Both are true. Let's see this question, like band gap, space band gap material is always preferred over the space band gap material for fabricating a space. Try to find this answer. If anyone is having doubt, let me know. Basically, we have covered like two type of band gaps, direct and indirect band gaps. So based on that, you have to answer this. And for your hint, I am giving you the hint that we have discussed about the photon and phonon. So based on that, you can, I think, answer these questions, because for solar cells, we would like to only have photons, don't phonons. So in the indirect band gap, in indirect gap, we are having also the phonons in the picture. So the horizontal motion of the is connected to the phonons. Okay, so we don't like that. So direct band gap is always preferred over indirect band gap for fabricating a solar cell. Question number 5 is that conductivity of n space semiconductor depends on temperature, its space, and hence the conductivity can be changed by subsequently doping this material. Anyone? So let try to find this answer. Try to recall the data of previous slides. Let's take 2 minutes. If anyone is having doubt, let me know. So conductivity of the intrinsic semiconductor depends on temperature. Okay, because intrinsic is not having any doping material, so it's only depend on the temperature only, and its charge carrier concentration, and hence the conductivity can be changed to subsequent doping this material. If we dope that material with some doping, we can increase the conductivity, okay, and charge concentration also. So in a PN junction, band bending happen when there are options. Like for Fermi energy of two metals is exactly the same before joining is formed. Charge carriers are the same across the junction. Fermi energy varies across the junction when it is initially formed. The chemical potential of electrons on one side of junction is more than that is on the other side of the junction. So when the PN junction is formed, basically band bending is occur, because when we are forming the PN junction, the Fermi level will be same for the both P and N type. So the band bending will happen, and you can see the diagram like this. Okay, so band bending is occurring, so the Fermi levels will become same for both P and N. Now we have to label the graphs. We have seen these graphs A, B, and C. So the equation and profile you have to relate. The correct option is the charge density is for A, the electrical field is for B, and the potential is for C. So there's the following. So float zone process is having moving RF heating coils, and the Tucholsky process is having fixed heating coils. Okay, and the Tucholsky process is having like primarily shape limitation due to the surface tension of liquid, relative minimal limitation with respect to size. But the float zone process is having both shape and size limitation due to surface tension of liquid. Now the ninth, arrange the following in increasing order of the disorder. So we know that the single crystal is having less minimum disorder. Then after that, the small size crystal material, and then amorphous material. Then the process which is used to manufacture PN junction by enabling gaseous element to condense on surface of the substrate under high vacuum. So basically, it is epitaxy process. Okay, I think I have covered all the questions, and I'm stopped presenting. Yeah, thank you everyone for joining this class, this live session. I will share the recording of this session, and I will also share the PPT to the NPTEL team, and they will provide you the link for the recording and for the PPT. Those who were not able to join can see the recording and can see the PPT. Yeah. Are you saying anything? I'm not able to hear you.
No, yeah. Your screen is not visible, but okay. Not to refresh. But there is some problem with presentation. Sometimes it goes off.
Yeah, okay. Maybe due to some maybe this Teams was having issue, so let me check today, because earlier it is not having issue, today only. So I will update the software. Maybe that will solve the issue, I think.
So one thing, question is in mind. Oh, why intrinsic type semiconductors are used? Because they are very less effective. Where these are used, intrinsic type semiconductors, mostly extrinsic type, no, P and
Yeah. Mostly we use extrinsic only.
Yeah.
Yeah. When we are talking about solar radiation, na, then we use extensing only. Okay, because due to that band gap. Okay, we can vary that band gap. Okay. Maybe the intrinsic semiconductor is used in some electronics. You need to look it in some reference books.
And second thing, amorphous type of these are semiconductors are basically they are to be categorized as intrinsic type semiconductor because there no any doping is done in amorphous type. We can say they are intrinsic type semiconductor, amorphous, all amorphous. We can say like that.
No, amorphous is basically structure actually, na. The single crystalline, polycrystalline. We are not talking about intrinsic or extrinsic. These are the structure only. We are
Okay.
talking about the structure. Structure of the like silicon is a material, okay? So you can develop the silicon in single crystal, polycrystalline, or amorphous. So this is the structure of the crystalline. It's not about doping and all. That is both different actually. Okay.
Okay. So amorphous silicon can be also be doped, no? With either
Yeah. Either in phosphorus, boron. Yeah.
Can be doped with, no? It will
Yeah.
have
Right.
less efficiency. It will less efficiency like that. Okay.
Yeah. For the efficiency, I need to check the actually books, but the amorphous part now you were asking. So it's just only for the structure purpose. Okay.
Yeah.
For
And
single
next
crystalline,
exercise, there was a question relating to structure and efficiency. So that's why
okay.
I was curious. In the next, can say next exercise.
Okay,
Next
actually, we
module.
are no. Actually, we are not allowed to discuss the question that are in next exercise. Actually, it's your for assignment.
Okay.
So
Okay.
it's better you don't ask those questions in this class. Actually.
And that's okay, but the concept wise, I was doubting on that. Okay.
Yeah.
Right.
Okay. So in
We'll
next
discuss
in
at
next
that
class,
time.
I will in next class I will clear that doubt. Okay.
Yeah. Right. Thank you. It was a very useful session.
Yeah, okay. Thank you for joining. Yeah.
Thank you.
Okay, everyone. Thank you for joining the session, and I hope you will all be there in the next session also next Monday 6 to 8. Okay. Thank you, everyone. I am ending the meeting. Thank you.